Hello and welcome to the fourth tutorial. This time we try to plug everything together and calculate the thermodynamic properties using Phonopy. Again, we start by opening a new notebook, and I now name my notebook Phono, and start by importing pyiron import project. Create our project, similar as before. Okay, and now we create our structure again. So let's see, sure. Bulk, and again we go for aluminum. At this point we choose just a primitive structure because we're going to do quite a lot of calculations and we want to keep them as cheap as possible. So we go with a single atom cell. Good. Now open here the project. Maybe to structure the notebook a little bit more, I will create a few headlines and then we can fill these headlines with content afterwards. So we will start by doing a minimization. Afterwards we do the harmonic approximation. And then finally the quasi-harmonic approximation. Good, and maybe we still have time at the end. We could also look again into concentration dependence. Good. To further structure those a little bit, so here we would need a bulk calculation. Bulk. And then a Phonopy calculation. And we can just copy these two. Just copy them here and paste them here. Right, so also for the quasi-harmonic calculation, we would do bulk calculations at different volumes, and then we do Phonopy calculations at different volumes. Good. So let's jump right into it. Create our first job. Minimize, mini, and we use lems because it's the only feasible solution. Right? So you could also do the same with DFT, but that would take much longer. So here we will just use lems. Okay. Now we create some more cells below, just so that we can fill them in. We assign our structure. And we can look at the different available interatomic potentials. We can select one, and here I just choose the first one. We just store this in a potential variable. And then we can remove this part, and here we just say potential equal our potential. Good, we want to do a minimization. In particular to optimize the lattice constant, so we calc minimize and set the pressure to 0. And then we can start our minimization. Mini dot run. And the minimized structure we save to a new variable. So we do the get structure method here, and by default, so get structure will take the last iteration step, so that's fine. We don't need to add any parameter. We can briefly paste it here just to compare. So we see that they're slightly deformed. That's only very minor, and then the cell dimensions. Good. So the structure is now minimized, so we come to our harmonic equation. We start with our bulk equation. So we define our job template. Again, it's SLEMS. Job name, we just choose LP. Or we can even move the template up. So here the bulk. Sure. Good. We create our template. We assign our final structure. And it's a template structure should be equal to the structure mini. That's what we want. And we define our potential. That should be equal to the potential that we just stored in there. Good. Now we can do our bulk calculation. So we name this bulk. We use our template job. And then again, using the copy2 function, we create a new job name, a new job name, bulk here, or this, and then the new database entry is false. And then we can just run this new calculation as it's by default as the static calculation. Good. Now we come to our Phonopy calculation. Here we again use our job template to create another master job. It's like similar like we did it in the last tutorial with DFT. Use our template, apply the create job function, and then select the job type. And here we do the Phone job. Create our job. We can briefly look at the input of this job, but we don't go into the details here. So you can change the interaction range that basically defines the cell of the supercell, the frequency factor, the displacement that we do, DOSMET, and the primitive metrics. And we can just execute now. Let it run. So take a little while. We can already look at the job table here. And you also see it here on the left, right? So we already did 3 calculations and we started to create our part and the LEMS calculation inside the Phonopy job. Phonopy job also offers built-in features like directly plotting the density of states. So that's something we can do. Get this nice density of states or frequencies. But here we are more interested in the thermodynamic properties. Right, so we can use our Phonopy job and say we import NumPy, MP, and we create a Kelvin space again. Start at 0 Kelvin, and let's say we go to 800 Kelvin, and we do 41 steps. And so then we have a 20-step interval. So that's our temperatures. And now we can use get thermodynamic properties. You see, I see always just use the auto completion to fill this, and we name this thermo. So here now we have our thermodynamic properties, so heat capacity, for example. We now want to visualize this. These as well with matplotlib, so import matplotlib. Matplotlib pyplot, spt, and we can do plot. We take our temperatures and plot the heat capacity. table and PLT1. Paste. Oh, again, made a mistake. To see our heat capacity. And we also can calculate our entropy for the system. And then to calculate the free energy, we basically use the free vibrational free energy that we get from Phonopy, and we add the bulk energy from our previous calculation. So we have our bulk here, and we can just go to the output, generic energy touch, and just take the last energy. And so we add this together, our bulk energy, here the free energy. Yeah, I should also make entropy, right? Entropy. And the free energy. Good. So this is the harmonic approximation. And the next step is to do the quasi-harmonic approximation, so adjust the volume with the temperature. And that's what we're going to do here. So this means we don't need a single bulk calculation, we need multiple ones. So for this we use the Murnaghan job. We again use our template job, which we already defined above. And we apply the create job function. Job type. Select our Murnaghan. And run Murnaghan. We can briefly look at the input parameters. So just for, as we already discussed, you can modify them. We discussed in the previous tutorial. So here at this point, I just run the calculations. And we'll again start for the different strains, the different calculations, so that we get the results here. Good, this will take another minute. Perfect. So we can just to validate that our volume, equilibrium volume is contained in the, oops, in 0 here. Just plot it like this. See our nice fit. We see we're very much centered around the equilibrium volume. Now we want to create the quasi-harmonic calculations. For this we again create a Phonopy job. Quasi, and this should be just. No, we again want to use the job template. And from the job template we create job. Okay. Phonopy template. The settings are again the same. We don't modify them. And now we can create the quasi-harmonic job by applying the same trick. So we can now use the create job function, apply it onto the Phonopy object, and use our quasi-harmonic job. If we now look at the input of this calculation, you notice that this first part is really quite similar to what we have in the Murnaghan. So we do 11 points, so this has to be adjusted, then they match with the Murnaghan points. This is the case here. The volume range 10%. We can again look here. Here we also have 10%. The start temperature and the end temperature, so that's something we want to adjust. So the end temperature should be 800 Kelvin, just to match what we also have here for the harmonic calculations, right? So we go to delta 800 Kelvin, so we set this to be 800 Kelvin, and the temperature steps, we set them to 41. And so we just copy paste here, 41. Just to match our lin space of temperature that we have. We can skip the cell again, you see that these parameters changed. And then we can already run the calculation. And this will now create for the different strains, always a Phonopy calculation, and then execute the phonons for this given strain. So this can already take a couple of minutes depending on the load of the binder system for these calculations to finish. You can already imagine, right? So if we now would do the same calculation with DFT, each calculation takes a little longer to really scale to being a day of work or even more. With using interatomic potentials, we can really develop this protocol just very quickly and then switch to DFT only once we know that these are really the calculations we want to do and the ones we want to fix. Good. This one finished as well. So we can now look at our job table, and we see we already did quite a few calculations here in this project, right? So we covered 39 calculations. I guess it's quite nice. And we can now analyze our object. So we start by browsing it and see the output. And then go directly to the output group. And then you see the different quantities. Let's see, we look at the free energy. We want to look at the shape of this. Yes, shape. I missed the energy. So this is our free energy. And now we can do the shape. And we see this is 11 by 41. So we have 11 strains, and then we have 41 different temperature steps. So what you would now typically do is plot the free energy over volume for the different temperatures. So that's maybe something we can also do here. So we can have our free energy, and we may want to have the volume and also the temperature. In a for loop, and for this for loop we combine the information that we have here, combine the free energy as transposed. We need to structure this a bit more nicely. We will do it like this. That's reasonable. Let's see. And then we can at least put in here the other two quantities. So we also want the volume. So volume is also given. Had the full list here already. Alright. So we just remove this. See here we want the volumes and the temperatures. Volumes and then And then always we want to plot it. Plot volume energy, and as a label we can take the NP unique from temperature, because it should be just one, and we do an NP round to have just the second digit, and we should convert it to a string because it's a label. And this is now not just the vibrational component. Should maybe take here just the zeros component. We don't have the brackets. And so we now want to, for our free energy, we want to add from our Murnaghan calculation. So let me check this again. So the name should be Murn. Yes. Murnaghan also has an output. And we can here take the E0 energy, that's the energy of our Murnaghan. And we can just add them together. So this is just the sum of those two energies, like we did for the harmonic approximation as well. And then we plot it with the free energy. And then we could now start to identify the whipping volume here and see how it's changing during the fits, right? So we did this already in the last part, so I don't want to go to the details of the fitting here. We can maybe show you one more feature of this class because it's already done inside. So we take our quasi-harmonic calculation, and then as part of the functions, no, there should be optimize volume. So here we need to put in the bulk energies of our Murnaghan. So this is the input parameter here. And if we do this, we already get the output. So this is the volume. And look at this function once more. Oh, there's no docstring. That's bad. If there's no docstring, you can always use 2 question marks to see the detailed output. And here we just copy it basically. Let's take this to look at the functions and have the corresponding output. And these are now the temperature optimized quantities, so we can again do the same plots that we did above. So we can now plot our temperatures, the optimized volume, label is no temperature, y label, and volume. And in the same way, we can also plot the same for the free energy. Let's say we can do it now for the G list and oops. Now it's free energy. can also do it for the entropy and so on. Check again entropy list and also the capacity list. Good. So now you saw how to apply the quasi-harmonic approximation, and now I want to briefly again show you how you would then do this for multiple concentrations. Right, so let's say we start with a list of concentrations that we want to look at. Here to make it simple, so we use 25%, 50%, 75%. And now we remind ourselves about the very first tutorial where we used the SQS job. And then there's, so we can now say we create an SQS job. Or let's say we just create the structure is already there. We should create a larger structure. So let's say we create at least a 4-atom structure. Lattice. There's the bulk. Let's say, and then we go for cubic. And we create our job SQS. Here, create job type. Again, the SQS job. Again, following the very same what we already did in the first tutorial. And now we would have like the FCC lattice. We could also, maybe that's better. And so I should rename this structure FCC. And we could also think about how to create a BCC structure for the very same system. Crystal structure BCC. No, there's no lattice constant defined, so that's what we have to do. And say we set the lattice constant just to be 3, just as a test here. So you would create an FCC lattice and BCC lattice, and for each of these lattices you would realize different concentrations. So here I just maybe I move this part down, right? So you would repeat the very same steps for the BCC lattice, but I will only demonstrate them now for the FCC lattice here. Right, so we would here do it for the FCC lattice. Good. So again, we assign the variables to our SQS job. So maybe we should also name this one FCC, oops, SQS, FCC, SQS job. We assign our FCC lattice structure, equal structure. And then we can go from here and look at our input parameters again. And we see, okay, we don't want so many iterations. So again, we copy this and limit the number of iterations to 1,000. And now we basically apply the same trick. So we use an SQS master job, which can be created from the SQS job. And it also has the create job function. And then we can go to job type, SQS master. We already saw there. And then we can, in this SQS master job, we can again look at the input. And this input takes basically two species and then a list of fractions. So the list of fractions that we want to look at here would be just the list of concentrations that we defined up above. And our list of concentrations. And then our species would be aluminium and nickel, for example. Right, so we can again just copy this. Let's say the first one is aluminium, and the second one might be nickel. Let me execute the cells. And with this we are set up, and we can run our SQS master job. And it will now start for each of the concentrations and a single SQS job. We can also take a look at this. And what we see here, so we started the different SQS jobs. And then we take our SQS master job and list the structures here. And this would now give us the different structures. So now we have the structure with the three concentrations. We save them in a variable. But what we would also like to have are the two end members, right? So we already created one end member. That's our structure lattice. And we want one more. That's basically the full same structure, just with all nickel. Or the other. Right, so here we just copy this, and now we set all atoms to switch the species. And with this we can build our list, and we can just add these lists together. We have our structure list that we just created, and then we also have the end member, the opposite lattice concentration. This total and in the same way you would have then the different concentrations. Right? So we have our concentrations total, and there would be 0 here, then the list of our concentrations, and then 1 here. And with this you have everything, right? So now you could iterate over those, you could add another phase like the VCC phase or other phases here that you might find. We always minimize the volume first and then calculate the forms in quasi-harmonic approximation. Right, so it's all basically using the same principles that we already demonstrated previously in the quasi-harmonic approximation. Right? So we start by doing our bulk calculation around the equilibrium minimum. If we don't find the minimum in the first try, we maybe want to slightly adjust our guess and then try it again. Important, we always use here the already optimized structure for one lattice. And then we can do a quasi-harmonic calculation, again just plugging the building blocks together, and then you get the optimized free energy over temperature and volume. You get from there get the optimized volume, optimized free energy, entropy, and heat capacity. And this data would be then stored in a TDB file and could be then read in other tools like SPay and PyCathode. With this, I'd like to thank you for participating in the 4th tutorial. I wish you a lot of fun with the exercise, and see you later. Bye!